Okay, so this is lecture 18, the last lecture before the 2-week break. And it's about finite differences also, but now these are differences, finite difference methods for problems that are moving in time. And the key issue becomes stability. As we move in time, do things blow up or not? Well, of course, we could ask the same thing, and it's the classical question for the differential equation. Does it blow up? The solution blow up? And what does the answer look like for that? So here's an ordinary differential equation. I start at some u of 0. What's the solution to that equation? Well, it's constant coefficients. The model is to understand what's going on with constant coefficients and then apply that understanding locally. If the problem has variable coefficients, some c of x coming in, or if the problem is nonlinear, then still we hope that locally in a small neighborhood, the linear constant coefficient information is the key. So let's develop that. Okay, so now I could write the solution here. So this is the stability of the differential equation, just to be sure we got that straight. So the solution is what? U at time t is e to the a t u at time 0, right? So the condition for stability for non-growth of this is what? A less than 0. And if a were allowed to be a complex number, that condition would become real part of a. So the condition is real part of a less than 0. In other words, for the differential equation, for exponentials, where this is the OK region, the stable region. This is stable for e to the at. Always here, I'm drawing the complex plane, real and imaginary parts. So it's the left half plane is the stable half plane. Right? E to the minus 6t goes to 0, of course. Now, what about if we're moving? Now I'm going to ask a similar question and get similar picture for let me take the very simplest finite difference approximation to this equation. Prime is d by dt. Okay, so how could we approximate that by finite differences? Well, let me just do the natural thing. U at step n plus 1 minus u at step n over delta t is equal to a u at step n. We're just in things are changing in time. Now the t is now changing to a discrete variable n, and of course u0. This is u0. And we hope that un should be would be roughly approximately the true answer at what time? If we take these time steps one at a time, very fast, very quick. After we've taken n time steps, what length of time has expired? N delta t. So each time step was a delta t. So we would hope that un is like the true answer at the time n delta t. And we, of course, have in mind this convergence as delta t goes to 0, but n delta t goes to some fixed time. So this is convergence at t, let's say. Delta t is going to go to 0, but the product n, so of course it takes more steps, but to get to the right time. Okay. Okay, so this is, if I rewrite this, putting un plus 1 on one side multiplying up there, bringing over the 1 plus a delta t un. Is that what is happening? And of course, so two questions. One is the stability. So let me ask you about the stability. When will this difference equation be stable? So the difference equation is multiplying at every step by that number. So the requirement will be that that number should be less than 1. So we now, instead of a half plane for exponentials, for powers, we naturally have, maybe I'll draw it in the same thing, we have a circle for powers. This is powers, where this was for exponentials. Right? The basic. So something should be stability, this thing should be less than 1. Now, actually, what is actually, this is very good right away. What's the condition for this thing to be less than 1? If a is positive, it's not less than 1, right? If a is positive, then this is bigger than 1, clearly. And it's unstable. But we say, okay, can't help that. If a is positive, then the differential equation was unstable. So, of course, the difference equation, which is pursuing it, has to grow too. So we're okay with that. What we don't want is for a to be negative, a perfectly stable equation, and then our approximation is 1 plus a negative delta t, so it's smaller than 1. And we would be very sad if it was bigger than 1, because then our approximation would be blowing up when the true thing is going down. Now, can that happen? Could this quantity blow up on us for a negative a? It could. It could. Because how would that happen? If we try too big a time step, and we have a negative a, like -6 or something, then what's going to happen? If that time step is too large, delta t is too big, this 1 minus 6 delta t, well, what's the problem? Yeah, it goes the wrong way. It goes below -1, and we're blowing up. We're out of the unit circle. We're blowing up. So we need 1 plus a delta t should be smaller than 1. Well, that just means a negative. But also we don't want it. We want it to be between -1 and 1. So this requirement, what does this then tell us? That's a true requirement imposed in the difference equation by just sort of, you can't be too fast. You can't take big delta t's. And of course you would like to take delta t big, because you maybe want to know what's happening to the solar system in a zillion years. And you don't want to go, a second at a time. We would like to take delta t large, but this is quite a definite requirement. What does that requirement amount to? Let's see, if I put the 1 on the other side, now if a is negative, somehow a delta t has to be, what the magnitude of that, if a is negative, anyway, somehow there's a 2 in here, right? Delta t, yeah. Negative 2 over delta t. Is that what? Yeah, I'm probably standing right in your way here. Anyway, everybody sees it. All right, that's right. Yes, that would be one way to write it. Yeah, negative 2. This delta t can't be bigger than -2 over a. Right. And dimensionally, of course, that's appropriate. A has probably the dimension of 1 over time, so that's a dimensionless quantity, and its size is what's crucial. Okay, so this is called Euler's method. I mean, it's the first method that would occur to anybody. And it's a quite strict requirement. And you really want to get away from it. I mean, for example, at MIT, there's a couple of really sharp guys. Jerry Sussman, kind of a character. And what's his buddy's name? Jack Wisdom. So they really, I thought of the solar system thinking of them because they established that the solar system was chaotic. And they established that by actually computing the evolution of the solar system for eons. And of course the danger is, I mean, I don't know exactly how they did it because first of all they had to stay stable or forget it, but they also had to stay accurate. And of course as I move forward with this discrete thing, mostly the errors tend to grow on me. You know, if I'm, you know, what is this method doing? The true answer is some e to the at, and I better make it, so I'll start it at 1, and I better make it a negative. So a is negative, otherwise it's not stable. And what's this discrete method doing? It's Euler's method. It's chopping up delta t's, and it's taking here, and it's starting with the right slope, but it's linear, clearly. And then here it starts with the right slope, but you see it's overstable. So it's extra stable. It's decaying too fast, and that's better than the opposite. But it still means that in a few steps we will be not very accurate. So we would like to make this more accurate and more stable. All right, let me suggest a way to make it more stable. Use the new value, instead of the old one. So that's not Euler anymore. This is implicit. It's called implicit because the new u is implicitly showing up in both sides. And now this needs correction. And what's the stability condition if I do it implicitly? So let me write the formula again. Again, I bring up the delta t, but now I bring this over. So it looks like I have a 1 minus a delta t, un plus 1 is there only a un. So now, if I just divide by that to see what's going on, the new un, was that a 1 minus a delta t? Okay, what about stability of that one? If a is negative, what's that growth factor now? If a is negative, we're dividing by something more than 1. It's stable, unconditionally stable. No limit on delta t. Take delta t a million years, and you're stable. But of course, again, this won't be the same picture, but of course it won't be very accurate. So any astronomer is going to sneer at such first order methods. So astronomers create difference equations that are much more accurate. Well, we could take one astronomer's step and take the midpoint thing, or the Crank-Nicholson method, or whoever we want to give credit for, and use the average of those two as on the right-hand side. So now we've written up a third method. Is it implicit or explicit? Implicit. implicit because we got the new guy appearing on both sides. Of course, for a linear equation, that's no problem. We just bring it over on the other side, as I'm about to do. Un plus 1 is multiplied by a 1, and then a minus a delta t over 2. And then on this side, un is multiplied by a 1 plus an a delta t over 2. So, for this 1-by-1 linear system, of course, trivial. But, of course, we have in the back of our minds we have a system of equations, not just one. We have nonlinear equations. We have some right-hand side. This is the general thing would be some function of t and u on the right-hand side, and u is a vector. So I've got n equations. I've got nonlinearities, and when I go to evaluate, I have to put u into the function. Here, the function was multiplied by a, so that I didn't have any problem with. But now I have to substitute u in the function. If I want derivatives, I've got work. So implicit gives me a nonlinear equation. See, implicit would mean un plus 1 would be here, and it would also be inside f. So I've got work to do. At every step, I've got this nonlinear thing to solve. So implicit is time-consuming, but more stable. Explicit is very fast, but limited stability, limited time step. Now, what's the time step situation if I divide by that guy? What's up? And again, I'll take a to be negative because that makes the differential equation stable, so I've got a chance here. So I'm interested in the magnitude of this quantity now. Is it below 1 when a is negative? It is. It is. If a is negative, then this guy is bigger than this guy. So, and that's actually a good method. Now, can you see why it's better than the two previous methods? Any guess on that? So I haven't, we've spoken about stability, but of course there's another aspect of choosing the difference method, and that is somehow accuracy. Just the way, we're sort of centered here. We're sort of centered. This is, sorry? Right. Yeah. This is like centered around the halfway, and we know that this is a great. If I think of that as centered around the halfway, that's the center difference. That's second order accurate and all good. So it's a level of accuracy up, which I could see. Actually, I should show you. How would you test the accuracy? Can I compare these three? 1 plus a delta t un. That was our first one. And then the second one was 1 over 1 minus a delta t un. And the third one is this, 1 plus a delta t over 2 divided by 1 minus a delta t over 2. Okay, now I'm discussing accuracy. Now, how do I see the accuracy? Well, what am I accurate with respect to what? I guess I'm comparing with the true thing. So what is the true answer over one time step? What's the true factor that I should multiply by? If I go from 0 to delta t, what's the true factor? Oh, e to the a delta t, yeah. If I only went delta t. So these guys should all be somehow approximating the true e to the a delta t. That's what the real factor is, growth factor. And does your eye tell you right away that yes, e to the a delta t is approximated by that? Why is that? Sorry? It's the Taylor expansion, right? It's e to the a delta t starts out with those two terms if I expand out the exponential. And what about this guy? Well, if I do that division, let me just focus on these pieces here, on these growth factors. So I'll just look at the growth factors. If I do that division, what is that? That's 1 plus, this is the geometric series, right? 1 plus a delta t plus a squared delta t squared, so on. Okay, and how many terms have I got right there? 1, yeah. The constant's right, otherwise, like, forget it. In fact, this has to be right, otherwise. So consistency, the word consistency means at least I got this piece right, which came from the equation. To get this one right, have I got this one right? I'm off by a factor, so I don't have it right. I don't have it right. So it's only first order accurate. I only got the basic one right. I didn't get the next one right. And now this is a way to see that this centered thing is better. So what would this one be? This is 1 plus a delta t over 2 times this division would be 1 plus a delta t over 2 plus what? A squared delta t squared over 2 squared, right? It's just, the series is 1 plus s squared plus s cubed, so on. Okay, then I have to do out that multiplication and then compare with the true. Everybody is remembering that the true is a 1 over 2 factorial, a delta t squared, and 1 over 6 if I really was on the ball. So what do I get, how much do I get correct here? The 1, then the a delta t over 2 twice is a delta t, and then the a delta t over 1 times this is 1/4. Oh, look. Hey, it looks great. Do you see it? I get 1/4 out of this and 1/4 from the 2 1/2. So I have 2 1/4, 2/4 of a delta t squared. 2/4 matches the half, and it's correct. Yeah. So it shouldn't be a surprise that center differences bump the accuracy up by 1, which is quite important. I mean, that's a very big gain. From 1 to 2 is the biggest gain in accuracy. Okay. So you're seeing stability, you're seeing accuracy, and just to conclude my thoughts about ordinary differential equations, what would astronomers do? I mean, they would never ever settle for even second order accuracy because they'd lose their planet right off the bat. So they will use a much more sophisticated, this is just a 2-step, or I should say 1-step. This is a 1-step method. It's from old to new, 1 step later. So astronomers wouldn't just use the previous value, they'd use 8 old values. So that would give them the chance of, with coefficients that there are degrees of freedom, weights that they can choose. So they get to choose the weights that multiply all those old values, and they get to match the exponential 8 more terms. So those are so-called Adams multi-step methods. Or Runge-Kutta is a famous one. It's too complicated to write here, but it does several. It's a multi-1-step method. It repeats 1 step jiggles around and produces fourth order accuracy. So it's a definite success, Runge-Kutta. Of course, they all have stability requirements. Runge-Kutta will be unstable if A is too big, because it's an explicit method. Runge-Kutta, any explicit method has to go unstable for some A. A good method would go unstable later, would allow a bigger delta t, but eventually if it's explicit, you've just got a polynomial, and the polynomial is never going to stay below 1 forever. Polynomials don't do that if you draw their graph. So, so there's a lot of thought about ordinary difference methods, implicit, explicit, how to control the error, and maybe the MATLAB. So, do anybody use any of these codes? Larry Champagne in New Mexico developed good codes for prediction, correction, stability. He would decide on that order 8. If we're in astronomy and everything's extremely smooth, 8th order is great. But if we've got something that's jumping all over the place, to try to approximate 8th derivatives is fatal. So he'd back up on the order, and so it's very adaptive, and it's in MATLAB. I guess MATLAB has that software. So there's 2 or 3 competitive software. But you see what the developer has to do. He has to balance stability, accuracy, speed. Speed being how implicit you're going to make it. Yeah, it's a balance of all those things, and an adaptive balance. Yeah, it's quite interesting. You could say it's not as deep. Larry would probably feel insulted by this. But Pdes, partial differential equations, is like just more happening, because you don't have just a vector of numbers. We have functions. So can I move to Pdes now? Again, initial value problems. Maybe I start with a heat equation. So let me make my first start the heat equation, and then the wave equation would be a du dx. Okay, so now I'm ready for the heat equation. Okay, let's go explicit. Basic idea. Un plus 1 minus un, right, is A. Now we're going to be explicit. Basic. Okay. So what am I going to approximate the second derivative by? Well, everybody knows the 3-point second difference. So now these are un plus 1. That's the new time. I have to tell you where we are in time and in space, right? So I need a second index to say that I'm at position I. So what should we put first? Time first? Okay, so un plus 1, I don't know if it's more conventional, but time first, but let's do it. I minus un I. So that's over delta t. That's a time difference. And now we've got space differences here. So I'm taking them at time n. And I've got uxx here without the minus sign. So I should have un I plus 1 minus 2 ui n plus ui n minus 1. Good. Over delta x squared, of course. Sorry? Oh, did I swap? Yeah. So maybe that's my subconscious is telling me that I usually put time second. Nevertheless, for variety, we'll stay with that one. Okay. Okay. Does that blow up? Because we know the heat equation doesn't blow up, right? Solution to heat equation smooths out like mad. Has a maximum principle. It never goes above its starting maximum. That's our usual minus second difference. But now the heat equation's just UXX. Yeah. So hopefully I'm okay with that minus sign. And am I? Yeah. It's like I want something negative here now. Why? Just the way I wanted that A to be negative in this. Now A is positive. Let me take A to be, well, I'll take A to be 7 in my own mind here. Yeah, so A had better be positive, right? Otherwise, suppose A is a minus 1. Do you know about the equation du dt equal minus uxx? What's happening there? Is that a reasonable equation? Ut equal minus uxx? If I use the word backward heat equation, which is the right word, you'll probably tell me right away, does it sound reasonable or unreasonable? Unreasonable, right? You're trying to, yeah, this is describing diffusion somehow. And if you're going backwards in time, you're asking all this little gas back into this, into the, I'd say cigarette if that were politically correct. But back down the smokestack. Okay. Anyway, it won't happen. So ut equal minus uxx is wildly unstable. No, you never want to solve the heat equation in the wrong direction. Where wave equations are two ways. You could solve those forward and backward, but not linear ones. But not, okay. So A is positive. That's all that we agree there. A is positive. Think of it as 1. Okay, and now, but I do want something like negative multiplying it, because I want, so what's un plus 1 going to be? Un plus 1I is, again, I'll bring in uni, no, what do I do? The A delta t over delta x squared. That's going to be like the key ratio, right? Times uni plus 1 minus 2 uni and, let's see, I'm getting another uni from that. Sorry. What minus 2 plus something uni plus uni minus 1. You figure out what that something is, maybe. Whatever. Sorry? Is it delta x? Delta x squared? Oh, because that's what I'm, or maybe delta t. See, I multiplied up by, well, yeah. Who knows? Right. Okay. Now, my point is, it's okay. Oh, it's just, all right. Why don't I call this number something? And then remember what it was. That's the other part. A delta t over delta x squared. So we'll call that number just lambda. And then is this 1 over lambda? Is that? Okay. Great. Okay. Is that stable? Is this operation now I'm doing a whole time level at once, right? Here? Oh, so that I get, okay. I'm glad you're getting it right, because it's going to be, of course, highly important. Okay, doke. Yes, thank you. Thank you, thank you. This lecture would be completely on the wrong track if I don't have that right. Okay, first, now, what's going on here? We have, at every time level, we've got a whole vector of u's, right? At every fixed, at a fixed time, I say it, time 0, this is time going this way. Here's x. We've got all these u's at n equals, this is the n equals 0 line, and we're moving up a line to n equal 1. But we've got all these u's, so it's really a vector. This is a vector. U at n plus 1 is some matrix times u, the vector u of all the u's at time n. Right? And at every step, we're going to multiply by that matrix. So what's our requirement for stability? Eigenvalues smaller than 1. Right. Okay, so what's our matrix? Well, damn if it isn't close to being an old friend, right? First of all, it's minus. It's 1 minus 2, 1. So it's minus 2, but plus 1 over lambda, minus 1. So minus 1's on the diagonal, on the off diagonals, and that number on the diagonal. I didn't expect to get to this, but I seem to be there. So let me let you, so that's the matrix. That multiplies un. Oh, it is a plus 1. Yes, certainly. It's just habit that puts minus 1's off the diagonal. I can't adjust to that sign change, but time to adjust. Okay. All right. Okay. What about that matrix? What are the eigenvalues of that matrix? Oh, let me leave what lambda was here. A delta t. Everything is depending on this number. And what's the point? If that number is very big, if that number is big, that means, yeah, we're taking a big delta t, and that ought to somehow be dangerous. And it'll force me to use a small delta x. Right. If I take a big delta t, I would like to use a big delta t. What's going on? Yeah. Is that what I want? I want a limitation on delta t, yes. I'll tell you the answer. Always wise to tell you the answer. All right. The answer is that this number has to be smaller than a half for stability. For stability. And then it's got to come out of our eigenvalues, as we know. So that's an unpleasant requirement. Now let's think again through what that means. I take a little delta x for good accuracy, and then the delta t has to be extremely small. It has to be less than a half delta. If I set a to be 1, just to normalize, say, the delta t would have to be less than a half delta x squared, which is super small. So I'm only allowed these creepy little time steps. And this scaling of t with x squared, of course, is appropriate because it's t with 2 x's in the equation itself. So somehow, yeah, a half. Let's see. There is this lambda. Yeah. Why don't I? Sorry. Let me multiply that lambda in there. Shoot. I forgot lambda. That was the whole thing. Let me get this matrix here again with the factor lambda. So there's a lambda below the diagonal. There's a minus 2 lambda plus 1. Is that what's on the diagonal? And there's a lambda above. So just to write those numbers again, I have lambda, 1 minus 2 lambda, and lambda as my diagonals. And I claim that I need, why do I need, so my question is, why do I need lambda below a half? Is that old Gershgorin operate again? So what's the Gershgorin idea here? That all the circles are centered at 1 minus 2 lambda. So let me draw 2 pictures. One where lambda is less than a half, and that should be okay. And one with lambda bigger than a half, and that should be bad. Okay, so if lambda is less than a half, then 1 minus 2 lambda is positive. So my circles are here, so centers are there. And what's my radius? Yeah, so, right, so, yeah. So the center is there, and the radius is I add these guys to find the radius. So the radius is 2 lambda. So it reaches out to 1, which I expect, but it quits at wherever that is. 1 minus, where is that? 1 minus 4 lambdas? Yeah, that's where it stops, and it's okay. It's on the right side of minus 1. Where this guy is going to fail, because where's the center of the circle if lambda is 2/3 or something? The center, this is the center of the circles, and then the radius is the off-diagonal stuff is 2 lambdas. So center here, radius 2 lambda. Yeah. This is the good picture. The bad picture is lambda is bigger than a half, 1 minus 2 lambda. The center's over here. It still stretches up to 1, but now going back, it's gone beyond minus 1. In other words, this 1 minus 4 lambda has to be bigger than minus 1. That's the point. And that leads to lambda smaller than a half. Right. Okay, so the conclusion is, so this is like people just thought this stuff through well, this is earlier in the 20th century. It was recognized that there was a limit, that you couldn't just jump forward. Or maybe it was a guy named Richardson doing weather prediction that noticed that. And then, of course, what method did he naturally cook up? He wanted to stabilize this, so he cooked up a sort of midpoint. Crank-Nicholson or somebody, maybe Crank and Nicholson cooked it up, where this difference was half at the old time and half at the new time. You with me? It's going to be implicit, because I'm going to have new times on both sides of the equation. But I've centered it all and stabilized it. Good. Okay. So that's the story with the heat equation. The heat equation is very powerful because there's a restriction, delta T of the order delta x squared, unless we go implicit and save ourselves. Of course, if I make all this at time n plus 1, do you see the difference? At time n plus 1, all that negative stuff comes over here, becomes positive. I divide by it. It helps and stabilizes. You see the calculations here are not difficult. If we assume that, as I'm doing, that the boundaries are not our problem. We're in the middle. We're on the whole line, for example, no boundaries. And we just have neat little calculation here. Because our matrices are going on forever. So Fourier would say, wait a minute, you're using my methods, right? If we have these constant diagonal matrices going on forever, the reason we're able to do these simple calculations is that Fourier is correct now. Okay, and that's the model always to start with, the constant coefficient model. All right, could I now turn to wave type equations, where stability is again an issue? Okay, so to make this into a wave equation, I just make that a first derivative. So what ratio am I expecting now to be involved? Previously we had delta t. It'll be?
Just delta t
over delta x. That's right. This will be our new lambda. And depending on the method, we'll have some requirement for stability. There'll be some stability requirement on delta t over delta x to the first power. And if we go implicit, there might be no requirement. Yeah, so let's see. Can I fix up this? So now I have first derivative. So suppose A is now always positive. So keep A positive just so we know the sign of things. All right, what changes here for this equation? I just want a delta x. What else? Just a single difference. So just this minus this. I made it a forward difference. And what's going on in the xt plane? So I'm given all these starting values, and then this tells me how to get up to the next line. And what does it tell me? Where does that value? This is n plus 1 line, and this is n line. This is I position, this is I position, this is I plus 1 position. So what does it tell me here? I'm computing the new value from this value and this one. These are contributing to that new value. Right? And the question is, am I okay or am I in trouble? It should be just simple here. What are the weights? So I multiply by delta t, and that gives me the lambda again. Yeah, let me try again. I did such a bad job on this one, but you rescued me. So be prepared to rescue me again. This I just want to multiply up. So un plus 1, I, is some combination of un I and un I plus 1. And what are the weights? I multiply up by delta, so that gives me the lambda. So it's lambda. This looks like a minus lambda. This is a plus lambda and a 1. Is that? Seem reasonable? Ut is AUX. Oh, no, I didn't do it right. There's the I plus 1. Oh, come on. What are the weights? So there's the I plus 1. So the thing multiplying the I plus 1, let me start again. Yeah. Is it just lambda times the forward guy and 1 minus lambda times the... Is that better? Yeah. I just bring this up here, so let me clean it up and just put a lambda there. These should be n. Yes, that should be n. Oh, please. Should it? No, I don't think. I hope not. No, I brought the. Yes, maybe you're only. Yeah, maybe you're only making my life hard. Anyway, I've got time on my side here. Okay. Yeah, I think that's right. All right. And lambda is positive, of course. It's a delta t over delta x. It's positive. The question is it too big? Are we trying too big a delta x? So what's a too big delta x for this problem? Yeah. So each new value is this combination of old values. And I want to know, is it stable or is it blowing up? We could make a pretty good guess here. What's your guess? Lambda be less than 1. If lambda is less than 1, it's always greater than 0. This is, so your guess is that we're okay if lambda is, well, lambda is positive, not bigger than 1. Because in this case, these weights are both positive. It's sort of an averaging process. How could we go wrong? So it's true. But if lambda was 2, for example, then I'm taking 2 of this value and minus 1 of this value. And then at the next step, I'm taking 2 and minus 1, and you could feel that this is getting out of hand. But how would we pin that down? How would we pin that down? Well, von Neumann, who was the greatest mathematician of the time of the beginning of computer age, say the 50s or so. I mean, he worked on, he was at Los Alamos during the war. He was really fast. I'm sorry that I never met him, of course. But he is said to be just a lightning calculator, and deep, and interested in applied mathematics here. Then he became one of the members of the Atomic Energy Commission. But prior to that, it was his great pure mathematics. So just a fantastic guy. Maybe he's the last to have been sort of generally agreed by all mathematicians as the best at the time. I don't know who would, if there's anybody who would have that general judgment now. Okay, so he had an idea. His idea, well, it was Fourier's idea. He said, okay, we'll use Fourier. We'll suppose that U n I is, I'm a little sorry I've used I, because I'm going to need an I in e to the I something. If I use J, there might be some complaints. No? K? I'll use K as a neutral. Okay, so he said, well, put in an exponential. The thing is, you have constant coefficients. Anytime you have constant coefficient problem, you should put in exponentials. So he put in an exponential, say e to the I k some frequency, omega. And then he said, okay, that frequency is not going to change. It's going to come out. This will be. So then I get, what do I get then? When I plug that in, I have lambda at time n. This is e to the I k plus 1 omega, right? And then I have 1 minus lambda e to the I k omega. Good. Okay. To the n's. Well, okay, yeah, so I assumed that I assumed at time level n, I had a pure exponential. And I'm just taking one step. So I'm just looking at the growth factor at each step. So I could have started at 0 and asked you at 1. But I started at n, asked you at n plus 1. So what's the growth factor? The point is, e to the I k omega factors out, of course. So the growth factor is lambda. What is it now? Lambda e to the I omega, right? And a 1 minus lambda. That's the growth factor that multiplies. This is g, the growth factor. And it depends on omega. And when does our thing not grow? When the growth factor is smaller than 1. So von Neumann's requirement is, this is the von Neumann condition, the growth factor should be smaller than 1 for all omega. It's just the natural idea. Look to see what happens to an exponential. In any evolution problem, we look to see what happens to the eigenfunctions. They're like multiplied by an eigenvalue. Well, in a constant coefficient problem, the eigenfunctions are always these guys. So we're really doing that. We're plugging in an eigenfunction. But simple, exponential, we don't have to say that. We just plug in exponential. We get back exponential. That's why it's an eigenfunction, multiplied by some number g. Okay, now I just look at g. I plot g. So the requirement is g should be smaller than 1. Okay, so plot this thing now. Let me take lambda smaller than 1, which will be okay. Okay. What's the plot of those numbers then for all omegas? Do you see what's going on there? It's right. We start at some point 1 minus, here's 1. So here's 1 minus lambda. And then we have a circle of radius lambda, which always, it'll reach out to 1. But again, it won't, it doesn't, right, the radius is lambda. So in other words, the back end of the circle, the dangerous end, is now 1 minus 2 lambdas. Where the heat equation, it was 1 minus 4 lambda. Now it's 1 minus 2 lambda. Everybody sees this? That there's a fixed number there. And now this is lambda times e to the I omega. But what's e to the I omega? It's running all around the circle. So this runs around around this circle of radius lambda. And it furthest back is 1 minus 2 lambda, and that has to be bigger than minus 1. Because if 1 minus 2 lambda is below minus 1, we're in trouble. And now if I turn that around, bring that 2 over here, the 2 lambdas, 2 greater than 2 lambda, 1 greater than lambda. Win it. We got it. So that's the von Neumann idea. 1 greater than lambda. Put in an exponential. So now I only have one more minute. So this is the good method. Put in an exponential. I could tell you about, the book will, about other difference methods. We picked the simplest. We picked the simplest difference method. We could have used implicit. We could have, try implicit. Probably that's more stable. We could have used halfway, centered. That's probably pretty stable. What do I want to do? The list of topics has included here, and sorry that letter L in lecture got submerged, has included also this great CFL paper which was way back, 1928, far before its time in a way, or it brought its time with it. And what was the point of their paper? Von Neumann had a more general method. Courant Friedrich Levy just made this observation, that we're computing this new value from these two. And they observed, the three of them, that if lambda was larger than 1, here's the idea. The finite difference method, this simple one, is computing this value from these two. But now, where is the true value coming from that goes there? Where is the true solution? What's it doing? So the true solution is u at x plus a t. A function like that will solve the equation. Now, I'm going to go fast here. I'm just going to say the answer. The true solution comes, so this ratio is delta t over delta x, right? If the true solution comes from a point there, the characteristic it's called, that would mean that then that would have slope 1 over a. See, the slope of this is, it's a simple idea here. The true value of u is coming from these values along some line. If that line is in here, then that's good. We're at least using good stuff. If the true value that's reflected up here comes from out here, we're certainly lost. So it's like this top, I could introduce the words like domain of dependence, domain of influence. That this value has a domain of dependence here, and if the true answer is coming from outside that, then of course it can't be stable. If I have,
if it's offset at all, with every time step, you're going to be moving the whole thing.
that's true. So a better picture would be to have a bunch of time steps. With delta t over delta x as the sort of steepness, and then this value is coming from these two. These are coming from these three. These three are coming from these four, because each one is coming from the two below. Because I chose this particular scheme. Well, because the true solution is like one-sided. Because the wave's only one-sided. If I did that, I'd have to be two-sided. But I took a one-sided equation, and I had a one-sided difference, and that was fine. But if I tried to climb too steeply, where the true answer is coming at some slower, at some, if I try to climb steeper than that, then fail. I'm going to leave it there as the... So this sort of insight gives you only a necessary condition. That if you're not using the right stuff, you can't win. Von Neumann's insight really pinned down stability by saying, look at all the eigenfunctions, which are the pure exponentials in a constant coefficient problem, and be sure g is less than 1. So this is von Neumann. And that's the right one to use. Right. And then I mentioned this Lax theorem, Lax proved that if it was unstable, you couldn't converge. Yeah. So that's like a theorem in function theory, that if it's stable and consistent with the equation you want, you will converge. If it's unstable, you won't converge. There'll be some starting values that mess you up. It's sort of evident here. In this case, the starting value would be that messed you up would be the bad value of the bad frequency omega that brought you outside the circle. And if von Neumann's condition is satisfied, all the omegas keep you inside the circle, growth factor less than 1, stable, convergent, and success. Yeah. So this, you see the difference between lecture 18 and lecture 17. Well, there was a stability in lecture 17. It was the stability of the iteration. It was steady. The time wasn't moving. It was the iteration count. Here we're stability of the time is moving. Yes. Last question.
Does stability also imply that the solution will be accurate? Is that what convergence means?
Yes.
That it'll be the same as the continuous differential equation?
That's right. That it'll converge to the right thing if your equation has approximated the right thing. So there's a requirement called consistency, which says that your difference equation copied the differential equation properly.
But the stability condition is the same as the consistency?
No, consistency says this would be consistent whatever lambda we took, because we're approximating the differential equation in a reasonable way. So consistency is usually easy to check. You never screw it up. But then stability, we would screw up if we took delta t too big. Yeah. So it's always this iteration, and do things grow or don't they grow, and are eigenvalues the test, and what are the eigenfunctions, is appearing over and over in these lectures. Yeah. So we get a 2-week break for all of us, and then back April the 5th, I think, and I'll look forward to it.